Welcome to the new quantum era. I'm your host, Sebastian Hassinger. Almost every conversation I've had on this show about neutral atoms, trapped ions, superconducting circuits, photonics, sits on top of the same quiet assumption that a qubit is the right unit of quantum information. Two levels, a 1 and a 0. The whole industry is racing to build more of them, connect more of them, error correct more of them. Today's guest has been asking quietly and rigorously for about 30 years whether that assumption is one we should be questioning. Before we get into it, this episode is brought to you by Qubits OK, a dedicated job board and archive research digest built specifically for the quantum computing community. If you're navigating a career in quantum, whether you're a PhD student figuring out your next move, a researcher trying to stay on top of the literature, or a hiring manager trying to find people who actually understand what a Rydberg blockade is, Qubits OK is genuinely useful. They send weekly job alerts filtered by over 400 specialized quantum tags, trapped ions, QEC, quantum ML, photonics, you name it, so you're not wading through generic tech job spam. They also run a daily archive digest that surfaces papers relevant to your specific research interests. Already about 100 archive authors subscribe. It's free to sign up. Just head to qubitsok.com. And if you're hiring, use the code newquantumera-50 for 50% off your first job posting. That's qubitsok.com, code newquantumera-50. Now, back to that question. Ivan Deutsch is a distinguished Regents professor at the University of New Mexico, director of the Center for Quantum Information and Control, and founding director of the Quantum New Mexico Institute. He did his PhD at Berkeley, joined UNM in 1995, right as Shor's algorithm landed and the field tipped from theoretical curiosity to something that felt urgent, and did his postdoc with the Nobel laureate Bill Phillips, which gave him an unusually grounded experimental intuition for a career theorist. With his longtime collaborator Poul Jessen, he spent decades developing the theoretical tools for quantum control of neutral atoms in optical lattices, work that laid intellectual foundations for much of the neutral atom industry that exists today. So when QuEra, Pasqal, atom computing, and Infleqtion are all building qubit-based machines on those foundations, and the field's most thoughtful theorist of neutral atom control looks at that consensus and says, I think we may be leaving most of the atom on the table. That's a conversation I want to have. There's also a second thread here I didn't expect. For someone who describes himself as an ivory tower guy who's never left academia, Ivan has turned out to be a remarkably effective institutional builder, quietly assembling something in New Mexico that has almost no parallel anywhere in the quantum world. We get into that too. Here's my conversation with Ivan Deutsch. Ivan, thank you very much for joining me today. I've been, as you know, we started talking about getting you on the podcast at least 6 months ago or more. I think we actually talked about it even earlier than that. But one of the reasons I was really wanting to get you on is that you you joined, I think, University of New Mexico in maybe 1995 or early
Correct.
90s or mid 90s, right when Shor's sort of was creating a buzz. And just sort of, I would love to hear your journey from, PhD at UC Berkeley to position at University of New Mexico. What was quantum like in those super early days?
Oh, yeah, that's exciting. So, I finished my PhD at the end of 1992. At that time, we already started to learn. I did my PhD in quantum optics. I worked in quantum optics because I was interested in the foundations of quantum mechanics. And when I started my PhD in 1987, that was the time when Alan S. Bay did his experiment. And that's what got me hooked. And so I got into that. I was interested in understanding the foundations of quantum mechanics. And many of us in quantum optics, that's why we did that. And one of the things that was starting to happen around that time was a few ideas like quantum cryptography. And Arthur Eckert was kind of an evangelist. Would come to quantum optics meetings, and he taught us in plenary sessions about quantum key distribution and the like. I mean, BB-84 had already existed, but it hadn't really permeated the community. So we started to get the idea that, quantum information was a thing, that if we can harness the special powers of quantum mechanics, we could do things that were not possible if the world were processed according to classical. So I wasn't working in that area at the time. I was working on optical communications, sending information over optical fibers. I did my postdoc at France Telecom, actually. And and when I came back to the US in 1993, in 1994, actually, Arthur came and gave a colloquium at NIST, where I was a postdoc at that time, and told us about Shor's algorithm. And and NIST then hosted a conference, uh, invited Shor in 1994 to give a talk, and with a lot of the real early people in the field to talk about this. And I was blown away. I didn't, of course, understand Shor's algorithm, but I was very excited about the whole thing. And at that time, I was looking for a faculty position. And Carl Cades, who was one of my heroes when I was a student, and was here at UNM and contacted me that there was a potential opening. And so it's not, I was a big city guy, and moving to Albuquerque was a little scary. But this opportunity was incredible, and I was very, very lucky to get the position. And so I came to UNM to work together with Carl to build this program in quantum. We were one of the first. Carl was a real pioneer. And at that time, there was something that he called the information physics group. It wasn't called quantum information. It was really about this connection between information and physics predated quantum information. And people like Wojciech Zurek at Los Alamos and others were real pioneers in around 1990, late 80s on this. So that was that. And so that was before quantum error correction. It was just after Shor's algorithm, before.
Right, in that brief moment.
Yeah, exactly. And so, it all unfolded really quickly at that time. I remember, Howard Barnum, who was a PhD student at that time, came in and brought this paper on error correction to us, and we talked about it. It was all really an exciting time. So I, decided that that's the direction I wanted to go in.
Yeah.
And
I mean,
yeah,
obviously it worked well. You're still at UNM. So the program that you founded, you've been there for now 25
30
years, right? 30 years.
30
Amazing.
years. Yeah.
Amazing. So you made the transition from big city to the high desert.
Right.
Obviously UNM has its own strengths, but how big a role did Sandia and Los Alamos being neighbors play in the longevity, in the center of gravity?
Yeah, I mean, in those early days in the 1990s, Los Alamos was truly one of the most important places for the foundations of quantum information science. And, some of the luminaries, I mean, of course, there was Nil and Laflamme, and Zurek and the theory side. An unsung hero is Richard Hughes, who had a very early program in quantum key distribution and ion trap quantum computing in those days. And Los Alamos, we worked closely, Carl and I, with the folks at Los Alamos, and we would meet regularly. And that was a big part of it. At that time, Sandia did not have a program. Their program really was launched around a decade later in 2005. In fact, I gave a short course at Sandia to all the managers and the staff scientists uh, that was organized to kind of give people an introduction. And Sandia went in very, very rapidly and expanded their program. And they're probably the largest effort in all of the national laboratories in quantum information science and engineering is at Sandia. So that unfolded a little bit later, but that but that the the assets here in New Mexico between UNM, Los Alamos, Sandia is really, yeah, something that we feel is a real strength.
Yeah. You mentioned trapped ions work at Los Alamos. I had Dan Stick on not too long ago, maybe a year and a half ago, talking about his big enchilada
Yeah.
trap. Um, how did you, with the trapped ion work going on at Los Alamos, where was your transition into neutral labs? Because that's really where you've made a giant
Right.
splash in your research.
Yeah. So that's really what my background. So when I was a postdoc at NIST with Bill Phillips, Bill Phillips is one of the Nobel laureates who invented laser cooling, which was an important step towards being able to control, manipulate. Um, I was famously Bill's first and last theory postdoc. It's an experimental group. So I learned all about, atoms and laser cooling there. And I also met my good friend and longtime collaborator, Poul Jessen. He was one of Bill's students and he graduated around the time. And he and so Poul joined the faculty at the University of Arizona in Tucson the year before I came, and in the Southwest, that's next door. And to Albuquerque. And he reached out to me and he said, look, I'm going to write this review article on optical lattices. Optical lattices were a new idea of how it was based on Pohl's dissertation and what I worked on as a postdoc of how in laser cooled samples, individual atoms are trapped in the bright spots of an interference pattern of a set of intersecting laser beams. It's kind of an artificial crystal. And so Pohl and I at that time we were inspired by what was going on in ion traps. In ion traps, the work, really pioneered by Dave Wineland at NIST, the Nobel Prize winner in 2012 for his work on control of individual quantum systems. So we were inspired by that, and we said, well, we can do the same thing with neutral atoms rather than ions. And, there's a long story. The neutral atom, cold atoms versus uh, cold ionic atoms, they're kind of frenemies. The two they compete with one another. What's going to be the best clock? What's the most precise? What's the most accurate? There's a trade-off. Ions are great because they're charged, but you can hold on to them very tightly and you can manipulate them extremely precisely. But it's very hard to get but ions are terrible because they're charged. And because they're charged, you can't push many ions together in a single trap and they all talk to one another and you have long chains of them. Neutral atoms are great because they're neutral. And so you can get a ton of them together and you can get a million of them maybe in one optical lattice. But um but neutral atoms are terrible because they're neutral. And so how are you going to get them to talk to one another?
Right.
So I was inspired by what was going on in the ion traps. And Pohl and I worked very hard in those early years in trying to push the kind of technology that was being developed for ions to neutrals. That means being able to trap individual atoms and cool them all the way to near absolute zero, to near the ground state. Pohl did the first experiment on so-called sideband cooling in optical lattices. and the way in which we would manipulate control the motion of the atoms and entangle that with the internal states. So there were a lot of initial experiments that were done. And Poul and I, you know, worked together for 25 years in developing this. And so that's what happened. And one last thing I would say. So inspired by this, in 1997, I organized a workshop called Quantum Control of Atomic Motion, which had Dave Wineland, Rainer Blatt from the ion trap, and, a lot of the neutral atom people, like Hideo Nobuchi and Poul Jessen and others. And we hosted this series of workshops for 2 years, and that workshop became what we turned into a broader workshop called Southwest Quantum Information and Technology, which is SQuINT. And SQuINT is now in its 26th year as one of the bigs. So this idea of bringing together the ion trap and the tools and techniques that were being developed in ion traps for controlling individual ions, which was the foundation of quantum logic, we were transferring to thinking about
Yeah.
that for neutrals.
And of course, the interaction that you were saying is difficult to get with neutral atoms is critical because you need to get entanglement, you need to get 2-qubit operations, et cetera,
Right.
for universal quantum computing. So the Rydberg or Rydberg, I've heard it
Yeah,
pronounced
it's
both
Rydberg.
ways. I don't
Yeah.
know which Rydberg. Okay, Rydberg blockade is it's the excited state that you can put this neutral atom into
Right.
that allows you to do that entanglement. Was that part of did you were you part of
No,
that
we didn't have that idea. So that came a little bit later. The original proposal was one where we would excite the atom to a much lower excited state, and we envision but when the atoms are so the thing that's amazing about the Rydberg state is when the atom is excited to a very high lying orbital, the electron is barely bound, and it can feel the presence of an atom that is microns away. I mean, that's macroscopic from the scale of an atom, which is typically, orders of magnitude smaller. An angstrom is, 10 to the minus 10 meters versus, 10 to the third minus 3 meters, right? So if we were going to, I didn't know about Rydberg physics at that time. And I was just thinking, oh, we would excite them to a low lying excited state. But then we had to have the atoms very close to one another. And in optical lattices, that's possible, but it's much more difficult to manipulate the atoms at the individual level there. The Rydberg state idea followed on. It was a follow-on paper. And I don't think they fully appreciated the power of it. I know, so one of the co-authors of that original paper is my friend from NIST, Steve Ralston, who said, "Oh yeah, we just wanted to make the whole thing faster." Uh, and if if you're less bound, you have a much stronger interaction. So the original paper was called "Fast Quantum Gates." The true power of the Rydberg blockade wasn't appreciated, but it then became uh, uh, the thing. One of the ideas, though, that was amazing that has really panned out about the neutral atoms was the ability to be able to move in parallel large groups of atoms together. And that was an architecture we envisioned in the very first paper as a way of doing logical qubits in a way that you have a whole set of physical qubits that can talk to one another in a parallel way. And that is really panned out in the current, there's, for example, this new company, Aurora Atomics out of Caltech, where they really they've published a paper on their roadmap where they really emphasize this, and also other companies, of course, QuEra, Atom Computing, Infleqtion, others, where this ability to move atoms in parallel and bring them together in parallel. So a lot of the ideas were, I think, in the first paper. What we didn't have in the first paper was the power of the Rydberg level.
Right. Yeah. I
That was
find that
really, yeah,
that
Michel
plasticity
Lucan.
is so
Yeah.
exciting in that vacuum chamber. As you said, you can pack neutral atoms in. You might get 1,000,000 in one lattice potentially, and then you can rearrange them in space in all kinds of ways that seem to me to be almost like a magical ability to try different architectural patterns and implementations of error codes in all kinds of ways. So incredible role in setting the foundation for neutral atoms as quantum information devices or instruments. But I want to get to something that you're also known for, which is somewhat of a heterodox approach to using neutral atoms. People who are sort of learning about quantum computing may be familiar with qubits as two-level systems that where one level they're easily distinguishable, they're easily controllable one from another. But you're actually advocating for something you call qdit. So what is a qdit with a D?
Right. So, well, we can also think about about classical bits. We compute base 2. We have zeros and ones, and we have two-state systems, true or false, and binary logic as the way in which our whole digital information infrastructure works. And it's natural to port that over to the quantum world where instead of thinking about a bit, we have a quantum bit, the qubit. And we have two energy levels or orthogonal levels of our quantum state, 0 and 1, and that encodes our quantum information. But in principle, both in classical and quantum computing, we can have a different base. We can have base 3, and they sometimes called a trit. And we can have a Q trit, or a D level system where D is anything we like bigger than 2, we typically call a Q dit. Now, I don't think it's a slam dunk. I don't want to be an evangelist because I don't really haven't studied this well enough to be able to say, oh, we really should do quantum computation base 10 rather than base 2 or base 3 or what have you. But I think it's an important question, and a lot of groups are now taking this up. Are individual atoms or transmons and superconducting or even photons, we can, in principle, each one of them doesn't have to just encode two outcomes. It could encode D outcomes, D being whatever we might be able to get our hands on. Now, it's true we'd get more information density, but it's not a huge increase. I mean, it's a logarithmic increase. D to the power n versus 2 to the power n has log D over log 2 more information in it. So it's not that huge. And there's also the challenge you have to be able to now control not just a rotation on a two-level system, but a D-level kind of rotation. And we need to entangle these things differently. And we need to read them out. We need to be able to distinguish not just yes or no, 0 or 1, but 1, 2, or 3, or 0, 1, 2, or 4. And that's experimentally potentially a lot more challenging. However, what I think is the most important question is fault tolerance. So a quantum computer is, in my view, not going to do anything that is really powerful, something that we couldn't do efficiently on a classical supercomputer unless we have a fault-tolerant architecture, something that can error correct and do so in a way that corrects errors faster than we're making them. And it's not clear whether we can have a better threshold and a better architecture if we use QDITs. People have studied this for years. I mean, in the original, Daniel Gottesman famously invented the stabilizer formalism that is the basis of much of our understanding of fault-tolerant quantum error correction. It did QDITs in his thesis, in his paper. It was known, and people have in fits and starts looked at QDITs, but I think it's like everything until we have. I think the co-design aspect is important. There's theory and fundamental work, but there's also experiments. And sometimes when we see what the capability of what can be done in the lab is, we opens the door to new possibilities of what we might be able to do. And so, years ago, again with Poul Jessen, we didn't call them QDITs at the time, we called them large spin systems. And we developed the ways in which we can operate on and do arbitrary gates on 16-dimensional QDITs in cesium atoms. And this was work done about a decade ago now by Poul and before. These were not done, they were done in the ensemble. They weren't done in individually trapped atoms, and we were not entangling them at the time. But the tools that we developed then are now ones that are being applied. And I think, we're working on this now in new experiments with my colleagues at Los Alamos, led by Mike Martin, working on individually trapped strontium atoms, which have nuclear spins that are 10 levels. And so we call them QDecimals. And the ways in which we can do arbitrary 10-dimensional rotations and how we can entangle them. And I think there's a lot of work to be done there, even if we ultimately end up doing qubit-based quantum computing. I think these additional levels are ways, for example, where we might be able to efficiently encode a qubit in a QDIT and be able to have error correction in a way that is resource efficient.
Right.
So
Is
those are
that,
some of the
I
directions.
read something about that. I mean, by the way, I think it's phenomenal. I mean, one of the earliest thoughts I had when I was encountering quantum computing is, we're still doing binary. How do we know that binary logic is the correct approach in this totally new paradigm of quantum computing? So I've always been really, really happy that people like yourself are probing those assumptions and testing, what don't we know that we don't know, right?
Yeah,
So I think there's
absolutely.
incredible value in that. But I'm really intrigued by the idea of using the upper levels, so to speak, as means of encoding, of essentially instantiating error codes inside, like almost in the interior of the construction of the qubit. Is that equivalent in any ways to things like cat qubits
Oh,
or
absolutely.
dual rail
Right on
qubits?
target.
Right. Okay.
Right on
Yeah.
target,
Yeah.
Sebastian. Yeah. So in fact, we were inspired. So, the so-called cat codes that are used in so-called bosonic encodings, like in a microwave cavity, in a superconducting control, or in optical systems, you're using the multiple levels associated with the uh, so-called Fox space to have the redundancy that's necessary for error correction rather than multiple copies. And similarly, we can use the multiple energy levels within a single atom to have the redundancy we need. And in fact, we wrote a paper really led by my colleague Milad Marvian, who's an expert in quantum error correction, my student Shiva Prasad Omanakutan, and others. We wrote a paper about spin cat codes. So these are very much inspired by the kind of bosonic cats and using the multiplicity of levels to encode a qubit. But I want to come back to this point of co-design. So the codes are designed in a way that they deal with the most important physical errors that occur in the atom, and the codes are designed in such a way to not say, well, the error is just arbitrary. We don't know what it's going to be. But in almost any physical system, some errors are more likely than others. And how you use that prior information to create what's called a biased error correcting code. This is an idea that's old. We are borrowing it from people like John Pasqal and others, Ferris, who've looked at this, and the group at Yale. And so I think that's, again, another important aspect. I think the acceleration in quantum error correction has come because the experimental platforms have gotten so good that we can put certain things to the test. And then we say, oh, you know what? There's this feature that happens. So, for example, there's this whole story about leakage and erasure, whereby population leaks out of the qubit subspace into other levels. And if we can know that happened, that's actually a very powerful error correcting tool. And many architectures are now building their architecture saying we want erasures rather than bit flips or phase flips. So I think the thing of working together, my career by accident, not because I chose it this way, but it was because of the opportunities that just were available to me, were ones where I worked at the interface between theory and experiment. And that has informed my thinking so deeply about theory. And
Well,
I
Ivan,
think,
also
yeah,
in the interface between trapped ions and neutral atoms as well. So even between modalities, and also between university and national lab, and also even more recently between public sector and private sector in your role in Elevate Quantum. So I mean, I feel like you're constantly in the interfaces.
yeah, it's true at those interfaces. It's it's sort of interdisciplinary. I think bring together all those different modalities of thought, modalities of work, modalities of platform, their creation can happen there.
Hmm. Yeah, that's great. And I mean, I want to make sure that we touch on Elevate Quantum, because you mentioned Squint, and you also, in addition to sort of getting that convening going, and which has been going for 25 years, as you said, you're the founding director of the Quantum New Mexico Institute, which is really sort of part of the bootstrapping of Elevate Quantum, which is the only quantum focused tech hub, EDA tech hub in the country, I believe. It's an incredible, sort of leapfrogging from where New Mexico was just a few years ago in terms of the supply chain, the industrial development or industrialization. Is that is that something that, I mean, obviously, as you said, you're comfortable in the interfaces, you find ways to create and add value there. Was there a particular sort of motivation from an economic development perspective, or a workforce development, an industrial development perspective, that drew you to that?
Yeah. So, um, let me just say a couple of things. So, in 2018 or so, Carl Caves retired, and I stepped in as a director of the Center for Quantum Information and Control, CQuIC, which has been our longstanding center here at the University of New Mexico. And when I became the director, that was just on the beginnings of the development of the National Quantum Initiative, the NQI, which was passed in 2019, in December 2019. And at that time, it was clear to me, also seeing what was going on in the private sector with the likes of Google and IBM and the startups that were beginning to really take shape, that this industrial wave was coming. And I felt that it was important. New Mexico, as we discussed in the beginning of our conversation, I'm so proud of our track record. All of the students and postdocs that have come out and are the leaders around the world right now, that New Mexico in particular would not be left behind in terms of the benefits of the economic development. New Mexico is a very poor state in the nation, and there's been a lot of innovation here, but it hasn't really capitalized on it for its people. So that's one aspect. The other thing is I just feel it's a new. I'm an ivory tower guy. I'm in 53rd grade or something. I don't know. And I've never left. But, it's our field now is not isolated from industry. And I thought it was also important that for our academic and R&D that there was an industrial component to the activities in New Mexico. So I strongly advocated for that. And one of the ways we did that was to join forces with our friends and neighbors in Colorado, where we have longtime collaborations, particularly with CU Boulder and NIST in Boulder. And it was through that we formed this consortium that became Elevate Quantum, led by Zach Yerushalmi, who just stepped down, and there'll be a new leader there. But in any event, so the regional tech hub was a way in which Colorado already had a kind of growing and vibrant private sector. New Mexico really didn't. And we won the Economic Development Agency Tech Hub Award that you alluded to, and that got the attention of the state of New Mexico. And together with what was going on internally to UNM, we established the Quantum New Mexico Institute, the QNMI, which is a university-wide center institute here at UNM. It involves the School of Engineering, Arts and Sciences, the business school, all different elements of the university to really build this interdisciplinary activity, as well as a joint institute between UNM, Sandia National Labs, and Los Alamos, bringing together those assets. And that is real. We're proud of that. It's a real powerhouse. I'm happy to have established it. And Bob Ledoux is a professor here who in physics and astronomy, who is now the director of the QNMI, and he's really leading the efforts going forward. I'm, really focusing my efforts really in my research, but I'm continuing of course, in this.
I was going to say, I think people like yourself who can navigate those interfaces and bridge those interdisciplinary components tend to be dragged into administrative and leadership roles because it's rare, right? It's hard to do that. So I'm glad to hear. I know your heart is really on the hard science and the research side. So I'm glad to hear you're sort of clawing back some of your time to get back to the science, because I hear from everybody on the administrative side that it can absolutely swamp your ability to do real science.
It's an important job, and I think I'm very glad we have an excellent director here now who's 100% devoted to this activity, and I think it's really this has now attracted. There's a number of companies who are establishing presence here. Quantinuum, one of the leading ion trap companies, opened a new facility here in Albuquerque. QuEra is announced they're opening. There's a big venture studio that's supported by the state that they're establishing. QNect is a quantum uh, communications and networking company. They're building a quantum network here in Albuquerque, and there are others. And so I think that ecosystem is really accelerating now. And I also want to thank the leadership of the state and the city of Albuquerque, who really have see the potential for this. And there's big investments that are being made now in the state and in the city of Albuquerque and elsewhere. So I think New Mexico, um, well, as I like to say, New Mexico is a quantum state. So
it's quite the journey too, from being interested in quantum foundations, leading you into curiosity about quantum information and its role in understanding foundations, all the way to developing an industrial ecosystem around quantum technologies. That's
in
quite the
my
journey. So
wildest dream.
yeah, yeah. So is the next sort of step in your research to continue to work on the Q decimal sort of approach to
Yeah, that's one component of what
yeah.
I work on. I think I'm generally still I'm interested in foundations. I work on questions about quantum complexity and where does quantum advantage lie, and the role of noise in limiting complexity. That's a big area of interest to me. I'm also working with colleagues at Sandia on building the better components for neutral atom quantum computers, even in the qubit based way. And, I may be thinking about collaborating with some of the industrial partners as well. We'll see how that goes. So, um, uh, but at the end of it, my heart is with my students, whether it be in the classroom or in our supervision of research. That's where I feel I have really the most to offer.
That's fantastic, Ivan. If you do end up partnering with any industrial entities, they'll be very, very lucky to get you. And I know your students are already very lucky to have you. So
I
I
appreciate that,
thank you very
Scott.
much for your time. I'm really, really happy we finally got this conversation together, and it's been fascinating. Thank you.
Thank you so much for having me. It was a great pleasure, Sebastian. Be well. Bye-bye.
That's Ivan Deutsch. And I have to say, the moment that's going to stick with me is when he described the symmetry of the neutral atom trade-off. Ions are great because they're charged. Ions are terrible because they're charged. Neutral atoms are great because they're neutral. Neutral atoms are terrible because they're neutral. It's one of the most elegant ways I've heard anyone frame this essential tension between every qubit modality. And it captures something real about why this field has so many live bets in play. If this conversation sparked your curiosity about the QDIT direction, there are two resources I'd point you to. First, Ivan's 2015 Quantum Magazine interview. The link is in the show notes at newquantumera.com, which remains the most accessible public articulation of his QDIT philosophy and is worth your time even a decade later. Second, the IMSI talk on neutral atom quantum computing with neutral spin QDITs, also linked in the show notes, where he walks through the strontium-87 results in real technical depth. A quick word from our sponsor. If you're building a career in quantum or hiring for one, check out Qubits OK. That's qubitsok.com, the dedicated quantum job board and archive digest that filters by over 400 specialized quantum tags. Free to subscribe. And if you're posting a job, use the code newquantumera-50 for 50% off your first listing. qubitsok.com, code newquantumera-50. If you want more conversations like this one, honest, technically grounded, and willing to sit with the hard questions, sign up for the newsletter at newquantumera.com. I write about what I'm learning between episodes, and it's the best way to stay connected to what's happening across the field. And if you found this episode valuable, the best thing you can do is share it with someone who would appreciate it. A colleague, a student, someone just getting into quantum who needs to hear a voice like Ivan's. You can subscribe wherever you listen to podcasts, and all the links are in the show notes. Thanks for listening. I'm Sebastian Hassinger, and this has been The New Quantum Era. Theme music by OCH. See you next time.